Today we're going to learn about something called isotopes. Okay. So first we'll define it, then we'll talk a little bit more about isotopes. So isotopes are just elements that have the same number of protons, but they differ in their number of neutrons. And so all elements have isotopes. Okay. So up until this point, we've just kind of assumed that for each element, there's just one version of the atom. Okay. Well, it turns out that's not true. All elements have isotopes. So the example I'm going to use is just hydrogen. So if you take a look at the picture up here, so if we were to look at just a sample of hydrogen atoms that are like naturally found on our planet, those atoms can look three different ways. Okay. So the first one can just have one proton and no neutrons. Okay, so we call this specific isotope protium. Another type of hydrogen atom that exists has one proton and one neutron. We call this one deuterium. And then a third type of hydrogen atom that exists is called tritium. So it has one proton and two neutrons. So all elements have isotopes. Okay, so if we were to take a sample of hydrogen out there, we would give three different looking atoms. Okay, so it could look like protium, it could look like deuterium, it could look like tritium. Now, when we say that there's three different types of atoms, that doesn't mean that they're equal. Okay, so 33% of hidrogen isn't protium, 33 isn't deuterium, and 33 isn't tritium. It turns out it's like 99.9% of hydrogen looks like protium. Okay, so just one proton. Okay, and then really, really small amounts exist in this deuterium form, and even smaller amounts exist in this tritium form. Okay. Okay, so if you look at this picture, before you just mindlessly copy down the words, okay, what is the one thing all three of those atoms have in common?
Protons and electrons.
Okay, one proton. Electrons, true, but I'm really interested in protons right now. So they all have one proton, which makes them all hydrogen because they have one proton. Okay. What's different about them? Okay, the number of neutrons changes. So if you think back to last Friday, you probably took some notes where you filled out this table with protons have a plus charge and they have a mass of 1 AMU. Do you remember that?
Yeah.
Okay. Neutrons also have a mass of 1 AMU, and then we said electrons have a mass of 0 AMU. Okay. So only protons and neutrons have a mass. And they each have a mass of just 1 AMU, or 1 atomic mass unit. So protium just has one proton, so it weighs 1 AMU. Deuterium has one proton and one neutron, so 1 plus 1. So this one weighs 2 AMUs. And then tritium has one proton and two neutrons, so 1 plus 1 plus 1 is 3 AMUs. Okay. So each different isotope has a different mass. Okay. And that's how we tell our isotopes apart. Okay. We can't see inside the nucleus, right? We can't see inside and see how many protons and how many neutrons there are. So the way we're able to distinguish different isotopes for an element is we're able to measure the mass of those different isotopes. Okay, so from this point forward, we're going to change our rules a little bit. Okay. So up until this point, we were pretty much assuming that there's one type of atom, and we just took the average atomic mass and we rounded it, right? Okay, so we're officially changing the rule now. Okay, so now that we know that isotopes exist, we're going to try not to use average atomic mass as often, and we're going to really try to use the mass number. So just a refresher, mass number is just your number of protons plus your neutrons. And can you have half of a proton or half of a neutron? No. So since a proton is 1 AMU and a neutron is 1 AMU, those are whole numbers, your mass number has to be a whole number. Okay. All right, so how this works in the real world, go ahead and take a look at the masses on the periodic table. All right, what do you notice about the masses on the periodic table? Most of them. What do they all have? What?
They're all numbers.
Good. They're not whole numbers, right? They all have a decimal. So the way the periodic table works, this decimal, whichever whole number it rounds up or down to, is the most abundant isotope. Okay. And think back to hydrogen. It's like 99.9% of hydrogen exists as that protein. Okay. So if it's the most abundant isotope, you don't have to give the mass number because it's going to be the one that you assume. Okay. If we're looking at one of the isotopes that are less abundant, then you're going to see this kind of a format here. So like the name or the symbol and like a dash and a number. So carbon 14, this 14 is telling you the mass number. Thank you. Okay, and we say carbon 14 because carbon 12 is the most abundant isotope. Okay. So if we're ever talking about one of these isotopes that is not the most abundant, we have to specify that. So we specify that by just a dash in the mass number. So then if you're given the mass number like this, that's like our way in chemistry to communicate. We're looking at a specific isotope, and we're looking specifically at a less abundant isotope. Okay. And then from the mass number, we can get our numbers of protons and neutrons. Okay. So carbon, how many protons will carbon have no matter what? 6 all the time. And then this time to get neutrons, instead of going to the periodic table and rounding, okay, you're going to take the mass number given and just subtract your number of protons. So what's 14 minus 6? 8. Good. And that's where that number comes from. Okay, so we're just going to practice counting protons, neutrons, and electrons for 2 examples. So the first one is copper 65. So again, like this dash and a number, this is telling you the mass number. So it tells us we're looking at a specific isotope of copper. Okay, how do we find protons? Okay, and what is the atomic number for copper?
29.
Okay, 29 always, that one won't change. This time for neutrons, we are not going to do what we did in the warm-up, okay? So we're not rounding. The reason is, I'm telling you it's copper 65. Okay, so we're just going to take 65 minus 29, and what do we get? Good. Okay, so in this example, there's 36 neutrons, and no charge is written up by copper. So if there's no charge given, what does that mean? It's the same. Okay, it's neutral, so how many electrons? 29. Good. All right, are we feeling okay with this one?
Yeah.
Okay, now on the next one, I'm combining our ions from Monday and our isotopes. So if you can get this next one, you're in a great spot. Okay, so we have chlorine with a -1 charge and this little dash 36. All right, so Cl is chlorine. So how many protons will chlorine have? How many?
17.
Okay, good. So chlorine has 17 protons no matter what. Okay, neutrons. How are we going to figure out the neutrons? Okay, we're going to use the mass number provided and subtract 17 from 36. What do you end up getting?
19.
Okay, so then this atom has 19 neutrons. And then finally for electrons, is there a charge on this one?
Yeah.
Yes. What does that -1 tell you?
That's an extra electron.
Okay, good. There's got to be one more electron than protons. So how many electrons? 18. Good. So to figure out where the atomic mass comes from, I just have this example first, kind of like my analogy. So let's say I give you a chem test. Half of you get 100%, and the other half of you get a 75%. If I calculate the average on that test, it comes out to 87.5. However, did anyone in the class actually get an 87.5? No. This is pretty similar to how the average atomic mass works. So some copper atoms have a mass of 63. Some copper atoms have a mass of 64. Some have a mass of 65. Do any of them actually have a mass of 63.55? No. Okay. This number comes from calculating a weighted average. So today we're going to learn how do we calculate that average. You need to get down this equation right here. Okay. So you don't need those must knows, but go ahead and copy down that equation. So in order to come up with this number on the periodic table, this average atomic mass, chemists need to know, well, how many stable isotopes are there? Of those stable isotopes, what's the mass of each? And then what's the percent abundance? Like with all the copper atoms out there, what percent of those copper atoms have a mass of 63? What percent have a mass of 64? What percent have a mass of 65? So if we know those three things, we can calculate the average atomic mass. Okay. And the equation we use is just like this M1P1, where M stands for the mass. Okay. And P, think percent. All right, so what we're going to do, we're going to take the mass of the first isotope times the percent abundance of the first isotope. Okay. And then we're going to add that to the mass of the second isotope times the percent abundance of the second isotope. And then what do you think plus ... means? Okay, if there was a third isotope, we would do it again. If there's a fourth, we'd keep going. Okay, we're going to do one practice problem together, and then you'll end up doing 3 without me throughout the class period today. So rubidium, it's a soft, silvery white metal, and it has 2 common isotopes, 85 Rb and 87 Rb. Okay. This 85 and 87, these are the mass numbers. If the abundance of 85 Rb is 72.2% and the abundance of 87 Rb is 27.8%, what's the average atomic mass? Okay. So first, we just have to know the numbers. So 85 and 87, those are the masses. Okay. And then one last step before we actually calculate, you have to take this percent abundance and convert it into decimal form. I'm going to do this, like a decimal. How do you go from percents to decimals? Good. What do you divide by? Good. So you do that by dividing by 100. Or how many places can you move the decimal? Okay, so I'm going to say decimal 2 to the left. Whatever option works best for you is fine with me. Okay. All right, so then we're just going to use that formula. So the first mass given is 85. And what's the percent abundance of that one? Good. Good. Is this 72.2? You have to convert that. So you can either type it in your calculator and divide by 100, or you can just move that decimal 2 to the left. So it becomes 0.722. Then we'll add it to the second isotope. So what's the mass of the second isotope? Okay, 87. And what's the abundance? 27.8. What do you have to do to this percent? Okay, you've got to convert it back into decimal form. So move that decimal 2 to the left. Or if that is difficult, like that just doesn't work for your brain, can you always type 27.8 divided by 100 in your calculator?
Yes.
Sure. Okay. All right, then if I were you, I would enter in my calculator just like this. Okay, so go ahead and enter it in. Okay, 85.556. Okay. When we're talking mass, our unit is AMU, which just stands for atomic mass unit. And then for these, I don't want you to round to sig figs. Okay, so I don't want you to round. I'm afraid that if you round too much, we won't be able to differentiate different numbers. Okay, so you don't have to round. And then when we're done, we're just going to check our number. Okay, we have two ways to check, does this number make sense? So first of all, it's an average between 85 and 87. So if we're averaging those numbers, should our answer fit within that range? Okay, yes. Okay, so your number better fit in between 85 and 87. If you have a number outside of 85 or 87, what does that mean? Something's wrong. Okay, and then second, whichever mass has the higher abundance, that's the number your answer should be closest to. Okay. So if you look here, our highest abundance is 85. And is this number closer to 85 than it is 87? Yes. Okay. So that's the other way to check. If this is the most abundant and you're closer to 87, that would indicate that something went wrong in that calculation. And then that's basically it for the atomic structure part of this unit. When I see you on Friday, we'll start talking about nuclear chemistry. Okay. So just regular old atoms, just kind of a review, the three main parts, protons, neutrons, electrons. Protons are the important ones when it comes to identifying the element. Okay. Number of protons stays the same, and it is found from the atomic number. Number of electrons determines if it's an atom or an ion. If electrons match the protons, it's an atom, it's neutral. Okay. If electrons are added or lost, then it becomes an ion. Okay. And then neutrons determine the isotope. So that mass number is given if it's not the most abundant isotope.